Now, welcome back. Let's continue lecture 6 of the chapter 11 refrigeration cycle. In previous class, we discussed vapor absorption refrigeration cycle. Now, in this class, let's try to solve one example related to vapor absorption refrigeration cycle. Now, consider an absorption type refrigerator in which heat is supplied to ammonia generator by condensing steam. So, the source of heat for the absorption refrigerator is a condensing steam which is available at 2 bar and 90% dry. The temperature in the evaporator is to be maintained at minus 5 degrees C. So the target temperature which has to maintain in the evaporator is minus 5 degrees C. Based on this given data, calculate the maximum possible COP, right? If the refrigeration load is 20 tons and actual COP is 70% of the maximum COP, then find out the mass of steam required per hour. Assume ambient temperature as 30 degrees C. So based on this given data, we can calculate the required unknown. First of all, let's see what is given and what we need to figure out. Now this is the schematic of the vapor absorption cycle. What we are given, we need to maintain that temperature in the evaporator at minus 5 degrees centigrade, and the source of heat in the generator is a condensing steam which is available at 2 bar 90% dry, whereas the ambient temperature is 30 degrees C. So based on this data, we need to figure out what is maximum possible COP of this cycle. And then it says if actual COP is 70% of the maximum COP, then how much steam is required to produce 20 tons of refrigeration. So basically, how much is the mass flow rate of the steam so that we can produce 20 ton of refrigeration cooling load, in the evaporator, right? So what are given to us? We are given the source. First of all, we are given that's a condensing steam which is available at 2 bar. So from the steam property table of the saturated steam, we can figure out the temperature at this state. The temperature, if you read from the steam table, that would be 120.2 degrees C. Then we are given the TL, which is the temperature that we have to maintain in the evaporator, which is equal to minus 5 degrees centigrade or 268 Kelvin. And the third temperature is given as ambient temperature T naught, which is equal to 30 degrees C or 303 Kelvin. Now we have tried in the previous lecture how to figure out the maximum possible COP of the absorption cycle, which is a function of the three temperature: the evaporator temperature, ambient temperature, and the source temperature. So if we put these value of the three temperature, we can figure out the value of the maximum COP. And if you put those values, then the maximum possible COP is 1.756. Now we are given in part B that the actual COP is equal to 70% of the maximum COP. So if we put that maximum COP, and the 70% means 0.7 times this value, so that means the actual COP is 1.229. So once we have the actual COP, we know that the COP or the actual COP is equal to the actual refrigeration load or the desired cooling effect divided by actual heat supplied, which is also which we call the input, because here the source of input is a heat which is supplied as a condensing steam. So now we know that actual refrigeration load is given, which is 20 tons of refrigeration. So if we multiply that with 210, we derive that in our first class that 1 ton of refrigeration in terms of kilojoule per minute is equal to 210. So if we multiply that, then we'll get 4,200 kilojoule per minute. That's the actual refrigeration load. And we know the actual COP, we know the actual refrigeration load, so we can calculate actual heat supplied. So the actual heat supplied will be equal to 3417.4 kilojoule per minute. So this is basically the heat that we have to supply in the form of the condensing steam. Now that steam is basically in the form of the condensing, phase change. As a result of the that steam will condense into liquid, so that's a phase change. So that heat, basically this heat Qs is basically the mass flow rate of the steam times HFG, and we can read from the property table. We know that HFG at 2 bar from the steam table, and that steam is a saturated steam, that will be equal to this one. So we know the Qs, we know the HFG, so now we can calculate the mass flow rate of the steam, which is equal to 1.55 kg per minute. So that means about 1.5 kg of the steam is required in per minute in order to produce this cooling. So the source of heat is basically the condensing steam. So that steam must be supplied at this flow rate at this temperature of 120 degrees C. So then you can achieve that cooling load, right? Now, up till now in the refrigeration system, we have discussed vapor compression refrigeration system, vapor absorption refrigeration system. Now the last one is air or gas refrigeration system. Now let's discuss the gas refrigeration system. Now in gas refrigeration system, as you know, the working fluid is air, which is cheap, safe, non-toxic and non-flammable, right? Leakage of air is not a problem because it's not a pollutant or it's not hazard to human being. And moreover, the gas refrigeration system is basically designed or basically applied for the aircraft cooling system. So that means the cold air can directly be used for the cooling purpose. In case of aircraft, the engine already consists of high-speed turbo compressor, as we discussed in chapter 10, Britten cycle, where we discussed the jet propulsion cycle. In that case, we saw that in aircraft it already is equipped with the turbo compressor, so we don't need a separate compressor for the cooling system. So as a result, it can reduce the weight per kilowatt of cooling considerably, typically less than 50% of an equivalent vapor compression system. So that means, let's say if we need to produce, let's say 2 tons of refrigeration capacity load, then for 2 tons of refrigeration, if we try to build vapor compression and gas refrigeration, then gas refrigeration will be 50% less weight for the equal capacity. So that means that's very suitable for the aircraft, because in aircraft we need less weight. The other advantage is design of the complete system is much simpler due to low pressures, and maintenance required is also very less. Now let's try to discuss the aircraft cooling. The first question comes into the mind that even though the outside temperatures are very low at a high altitude, sometimes at very high altitude, let's say 10 kilometers above the ground, the temperature may be as low as minus 50 degrees C. So that means in spite of so much low temperature, we still need cooling of the cabin. Why? Because of these reasons. One of the reasons is large internal heat generation due to occupants' equipment. So because of this heat generation, right? And the second reason is the heat generation due to skin friction caused by the fast moving aircraft, because outside surface of the aircraft is moving at a very high speed. So as a result of the skin friction, the heat is generated. So that's why that's one of the source of the heat that we need to remove. Another effect is we call the ram effect. In ram effect, what is happening basically at very high altitude, for example, let's say at 10 kilometer altitude, the air pressure is very low. We call that pressure as a sub-atmospheric. That means which is very less than atmospheric pressure. Let's say at the pressure is 0.2 bar, and at that height the temperature is, let's say, 223 Kelvin. So that means when we will compress this air from this pressure to atmospheric pressure, because human beings are comfortable at atmospheric pressure. So that means that outside air, first of all, we need to compress up to 1 atmospheric pressure. So once we will compress this up to 1 atmosphere, then the temperature will increase. Let's say at 1 bar, the temperature will become 350 Kelvin or 80 degrees C. So that means we cannot supply that 80 degrees C to the human being. So that's why we need to cool down that air. This is one of the source. So that means a cooling system is required to cool down that air. The other reason is the solar radiation. If the aircraft is moving at very high altitude, because of the solar radiation falling on the aircraft, that's one of the source of the heat that we need to remove from in order to produce the cooling inside the cabin. Now let's try to understand how the aircraft cooling system is working. Basically, you're already familiar with the jet propulsion system, that in jet propulsion system, basically the jet moves as a result of the thrust, right? That ambient air entered, first of all, diffuser, and that in diffuser the air is called the ram air. So diffuser section, then it entered in the main compressor, so it first compressed, and then it enters that into the combustion chamber. Then from combustion chamber, the high pressure, high temperature gases drive the gas turbine and then the nozzle. So the thrust is produced. Now, how the cooling system is integrated with the main compressor? First of all, one part of the ram air is bleeded from here. If you first see the component of the aircraft cooling, the first component we call that the heat exchanger, right? Heat exchanger, and then that's called the cooling turbine, that's called the cooling fan. Now how it is working? Basically, one part of the ram air, this is very low temperature air. That air is like in below 0 degrees centigrade, very cooled air. So one part of that ram air is used as a heat rejection process or as a coolant, and after the compressor, now one part of that hot air is taken from the main compressor, right? So here then the heat which is obtained as a result of the compression is rejected to, this is like a heat exchanger. So this will give heat to that low temperature ram air. So this ram air will move from this one. So as a result here, we'll have much lower or the low temperature air. So that low temperature air will further enter into the cooling turbine. So as a result of the expansion, a very low temperature air can be produced, which is sent to the cabin. Now here we can use that air for many applications. We'll discuss that application later. Now that air, that ram air which is entered into the heat exchanger is allowed to move out. How? Because that turbine, because this is a high pressure air, so that high pressure air can drive another turbine. This is a very small turbine, right, which is driven with the help of that high pressure. The temperature is very high, the pressure is very high, but the temperature is lower. So once it is allowed to expand in that cooling turbine, the temperature and pressure both decreases, but we can get certain work output. So that work output can be used to drive a cooling fan. This is basically a forced draft fan which is used to expel that air out, because once that fan is operating, then here the vacuum is created. As a result of the vacuum, it makes sure that the certain quantity of the air should move into the exchanger, so that the heat rejection process, heat from this high pressure, high temperature to the cold air can be accomplished. So as a result, we can produce that cooling. Now once that cold air is produced, that cold air can be used to cool down the, let's say, food item inside the aircraft. It can also be used because aircraft, it's not used only for the passenger aircraft, they also use for the carrier or very special equipment. Sometimes we need to move the dead body from one place to another place. So basically it can also be used for very special application, in addition to produce the air conditioning inside the cabin for the passenger. It can also be used for many special application within the aircraft. So this is how basically the aircraft cooling is system is working. Basically the ambient air is used as a refrigerant, right? And similarly that air from the air compressor is basically high pressure, high temperature. So that high pressure and high temperature air give its heat to that ram air. And then again this is further expanded, because we read that expansion process give you the low pressure, low temperature working fluid. So as a result here we can have that refrigerant air as low temperature, low pressure, which can be used as a cooling medium. Now this was the how the aircraft cooling system is working. Now how can we convert this practical schematic diagram into theoretical diagram, let's say TS diagram? You can see basically there are four processes. One of the process in the refrigeration is the compression process, heat rejection process, expansion process in the turbine, and then this is the cooling process, I mean the heat absorption process. So basically four processes take place in aircraft cooling system. Now how to convert that refrigeration system into certain TS diagram or theoretical background? That cycle that deals the gas refrigeration system, that's called the reverse Britten cycle. It is also called a Bell-Coleman cycle, which is the cycle on which the gas refrigeration cycle is based. Now you are already familiar with the Britten cycle. What happened in the Britten cycle? You are familiar with that in Britten cycle, first the air enter into the compressor, then the combustion process, and then the expansion in the turbine, then the exhaust process. But this is the reverse of the Britten cycle, so that's why that's called the reverse Britten cycle. So what happens in that case, as shown in the previous diagram, that the first process is the compression in the main compressor, then the heat rejection. That heat rejection take place by using the two air. One was the ram air, and the one air was the air which is bleed from the main compressor. Then that's expansion in the cooling turbine, and then that cold air is sent into the cabin where the heat is absorbed. That heat could be from the passenger, from the food, from the equipment, from anything that inside the aircraft. So now we can convert that on a TS diagram. For example, that's a compression process. 1 to 2 is a compression process. So that's called the 1 to 2 is a compression process. We can say that's an isentropic compression. And then from 2 to 3, is a heat rejection process. So we can say heat rejection at constant pressure. Similarly, that's a expansion process in the cooling turbine, so we can say isentropic expansion. Similarly, that's the heat absorption process. We can say that's basically the cooling effect, heat absorption inside the cabin. So we can say the heat absorption again as constant pressure. So basically the Britten cycle operates between the two pressure range. That's the low pressure, another one is the high pressure, and 2 to 3 is a constant pressure process. Similarly, 4 to 1 is a constant pressure process. So that cycle is known as Bell-Coleman or reverse Britten cycle. This is basically the ideal cycle. Obviously, if we see the deviation of this cycle from the actual behavior, then what are the possibility? One of the possibility could be that expansion process may not be the isentropic. So that could be the, like, let's say, isentropic process, actual process. Similarly, that expansion cannot be isentropic. It could be like this one. It could be the actual one. And similarly, there instead of the constant pressure, there could be pressure drop. Similarly, here could be pressure drop, right? So these are the deviation of this, but we'll focus on the ideal Brayton cycle, reverse Brayton cycle. Right, now let's try to calculate various heat involved, various input or output involved in the reverse Brayton cycle. Let's say the first process is 1 to 2, right? Process 1 to 2. What is happening in that process? Basically, the gas at low pressure is compressed isentropically from state 1 to state 2. In compressor, we are giving work input for the compression. So the work input from 1 to 2, that's an isentropic. So let's say M, that's the difference of the enthalpy, H2 minus H1. And let's say if we assume Cp to be constant, which is also called cold air standard assumption, because for the air conditioning range, the value of the Cp is not varying too much, because the temperature, operated temperature for the air conditioning is not very high. So that's why we can assume Cp to be constant. So that will be mCp delta T. So T2 minus T1. Similarly, that's an isentropic process and cold air standard assumption is used. So we can use that formula. T2 by T1 is equal to P2 by P1 raised to the power K, gamma minus 1 by gamma. Sometimes we use K minus 1 by K, or sometimes the symbol gamma is used for that case. Whereas P2 by P1 is known as pressure ratio. You are already familiar with that. That's called the pressure ratio. So that was process 1 to 2. Now let's move the next process 2 to 3, which is a constant pressure heat rejection process. So in that case, the let's say Q2 to 3 heat rejection, that will be equal to difference of the enthalpy M H2 minus H3, and for the cold air standard assumption, that would be mCp T2 minus T3. Similarly, the difference of the internal energy S2 minus S3 for constant pressure process, that's equal to Cp ln T2 by T3. Since the pressure is constant, so P2 is equal to P3. Now the next process 3 to 4, that's an expansion process in the turbine. So for the expansion process, we can get work output from the turbine. This is in case of compressor, that was work input. So now from 3 to 4, that's work output from the turbine. So the work output from the turbine, that's equal to the difference of the enthalpy H3 minus H4, and then again for the cold air standard assumption mCp T3 minus T4. And again, since this is an isentropic expansion, so for isentropic expansion, we can write down that T3 by T4 is equal to P3 by P4 raised to the power gamma minus 1 by gamma, whereas that's equal to the pressure ratio Rp. So here we can get in terms of the pressure ratio. And the last process, which is 4 to 1, that's the heat absorption, which is also called cooling capacity or the cooling effect produced. So the last process is again constant pressure process. So the heat absorbed from 4 to 1 is the difference of the enthalpy or mCp T1 minus T4. Similarly, the difference of the internal energy for the constant pressure process is equal to Cp T4 by T1. So this is again a constant pressure process. So by using these concepts, we can calculate the work input to the compressor, work output from the turbine, or heat rejection, or the heat absorbed in the cabin, or we can also say the evaporator, you can say. So how to figure out the performance of the cooling system, the gas refrigeration system? Again, the fundamental definition, heat absorbed divided by network. So what's the heat absorbed? Heat absorbed was from 4 to 1, that was Cp T1 minus T4. Where what was the network? Because we are giving input to the compressor, we are also getting output from the turbine. So what will be the network output? Compressor input minus the turbine work output. It can also be obtained this way, or it can also be obtained network as the heat rejection minus heat absorbed, right? So that Cp can be cancelled out, and this is a similar process that we did in a previous chapter for the diesel cycle. For the Otto cycle, that we take common T4. Similarly, from the denominator we take common T3. Similarly, we take T4 common, right? And we know these are equal. This ratio is equal to this ratio, equal to this ratio, because we know that this value like P2 is equal to P3, similarly P1 is equal to P4. So that means this ratio T3 by T4 is equal to T2 by T1. So that means these ratio, this one is equal to this one is equal to this one. So that will be, this will be cancelled out, this will be cancelled out, this will be cancelled out. So the remaining will be COP will be T4 divided by T3 minus T4. So that means we can compute the performance of the gas refrigeration cycle if we know two temperatures, T3 and T4. T3 is the temperature at the inlet of the turbine, whereas cooling turbine, whereas T4 is the temperature at outlet of the cooling turbine, if you recall the previous diagram, right? We can also convert this COP in terms of the pressure ratio as we did in previous chapters, like for the diesel cycle, for the Otto cycle. Now this is the previous formula, from the previous slide, that COP was equal to T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Now just to rearrange, let's say if we put that value, T2 was equal to T1 times, because that T1 times pressure ratio gamma minus 1 by gamma. Similarly, we can put the value of T4, right? That was equal to, we can also put the value of T3. This was the value of T2 minus the value of T3. T3 was T4 times Rp raised to power gamma minus 1 by gamma. Then again we put the same value as it is. Now we can take common this one, this term we can take common, and what will be remaining? The remaining will be T1 minus T4. Similarly here it will be T1 minus T4. The above is T1 minus T4, so this will be cancelled out. So remaining will be 1 divided by Rp raised to the power gamma minus 1 by gamma minus 1. So final relationship is this one. So that means COP of the gas refrigeration system depends on the pressure ratio. If the pressure ratio is increasing, COP of the gas refrigeration system is decreasing. Now finally, let's try to solve a numerical problem related to the reverse Brayton cycle or Bell-Coleman cycle. Now consider air refrigerator working on the principle of Bell-Coleman cycle. The air enter into the compressor at 1 atmospheric and at minus 10 degrees C, because at very high altitude assume that the temperature is very low and the temperature is, let's say, minus 10 degrees C. Now in the compressor it is compressed to 10 atmospheric and then cooled to 40 degrees C at the same pressure in the heat exchanger. It is then expanded in the cooling turbine, it is expanded again to 1 atmospheric and then discharged to take the cooling load. Now the air circulation, the mass flow rate of the air is 1 kg per second, and the isentropic efficiency of the compressor is 80%, isentropic efficiency of the expander or the turbine is 90%. So based on this given data, calculate the refrigeration capacity of the system, COP of the system, use this property gamma is equal to 1.4 whereas the CP is equal to 1. So based on this given data, please calculate the unknown. Now this is the reverse Brayton cycle or Bell-Coleman cycle. 1 to 2 is the compressor, isentropic compressor, and then the heat rejection and constant pressure, then the isentropic expansion, then the heat absorption at constant pressure. So that means P1 is equal to P4, similarly P3 is equal to P2. So that's a constant pressure. This is but we are given in the problem, if you recall that we are given the turbine efficiency as well as compressor efficiency. So once these efficiencies are given, that means this expansion in the turbine is no more isentropic. So that's the actual one. So we have to consider the actual efficiency from here to here. Similarly for the compressor, let's say we have to consider the actual compression. So let's say instead of 2, the actual is 2 dash. Let's say that's 2 dash. Similarly, let's say this is 4 dash, right? That's 4 dash, let's say. Now these are the given values. So first of all, from the previous knowledge that first of all we need to calculate the unknown temperature, because we have assumed the cold air standard assumption. For that case, we need to calculate all the unknown temperature. Let's say if we don't assume the cold air standard assumption, then we have to calculate the enthalpy at each point. But now we have to calculate the unknown temperature at all the points. Let's start from the first state. At state 1, what we are given, we are given the temperature. I mean the air enters at minus 10 degrees centigrade and atmospheric pressure. And then come to the state 2. At state 2, we know the pressure. I mean that compressor compresses up to 10 bar, 10 atmospheric pressure, but we don't know the temperature, right? We can, since this is an isentropic process, 1 to 2 is an isentropic process, so we can use this formula to calculate T2. So if we put these values, that's 10, that's 1, so 10 is the pressure ratio. We know the T1, so we can calculate T2. So the T2 temperature after the compression, after the compressor, that's equal to 507.8 Kelvin, or in degree centigrade, that's 234.8 degrees C. Now let's come to state 3. At state 3, we are given that temperature is 40 degrees C, and since that's a constant pressure, so the pressure remains constant. That means the 10 atmospheric pressure. Now come to the state 4. At state 4, we know the pressure, but we don't know the temperature here. So we can use again, because that's again an isentropic process, isentropic expansion. So we can use that formula to calculate the unknown temperature T4. So if we put all the values, we'll get T4 is equal to 160.4 Kelvin, or minus 112.4 degrees C. Now we need to calculate T2 dash and T4 dash. We can use these efficiencies that are given for the turbine as well as for the compressor. And let's say the isentropic efficiency of the compressor is equal to isentropic rise in temperature, that means isentropic rise in temperature divided by actual rise in temperature. So we can put that value. So from here we know that efficiency is 0.8. we know the remaining temperature like T2, T1. The only unknown is T2 dash. So from here we can calculate T2 dash. So likewise we can apply for the expander or for the turbine. For this turbine, the isentropic efficiency is reversed to this one, the actual rise in temperature divided by isentropic rise in temperature. So here we know the T3, T4. The only unknown is T4 dash. So if we put all the values, we'll get T4 dash equal to 569 Kelvin. Now we have calculated all the unknown temperature. Once we know all the unknown temperature, the first one unknown is to calculate the capacity of that system. Now the refrigeration capacity of that system, or the QL, is H1 minus H4, and if we convert in terms of temperature, that will be MCP T1 minus T4 dash, because we have to calculate the actual one. So we have to put that temperature T4 dash instead of T4, this one, previous one. So that basically the cooling capacity is from 4 to 1. That's the theoretical one, the maximum possible, but the actual is now, because 4 dash to 1. So that's why I'm using that T1 minus T4 dash. So if we put all the temperature, we'll get that value equal to 87.5 kilowatt. We can also convert in tons of refrigeration by dividing with 3.51. So that will be tons of refrigeration. And the second unknown is to calculate the performance, COP of the system. Now the COP of the system is equal to the refrigeration capacity or the cooling effect divided by network. So cooling capacity or the refrigeration capacity is QL, and the network is WC minus WT. So again, if we put all the values QL, WC, WT, and we put the value of all the temperature, then the COP of the system will be equal to 0.51, right? So that's the end of this lecture. If you have any question, you can ask me in the MS team, you can email me, or you can ask me during the interactive session. See you in the next class.